Hello and welcome to the sixth lesson of our fourth unit, Graphing Quadratics, in our grade 10 academic math class. So today we're going to get introduced to the third and final form of the quadratic that we're going to be looking at, and it is called factored form, as you can see from the title. So as in other lessons, I would recommend you hit pause here and you copy down this information that you see I've already filled out about the information visible from the factored form of a quadratic relation. So hit pause, copy it out, and then I'll talk us through it, and then we'll get on to the two examples. Okay, hopefully you have it copied down. I want to highlight that the factored form of a quadratic relation looks like this, where you have particular pieces of information that are visible just from this form without having to do any type of math. The first thing, of course, and what I'd like you to note is that all three forms of the quadratic that we've been dealing with, whether it was vertex form, standard form, or today's new form, factored form, they all have this a value just hanging out front. And as we know, the a value tells us a couple things. If you have a negative a value, it means that you are going to have a vertical reflection across the x-axis, essentially a parabola that opens down, versus a positive a value, which would have a parabola that opens up. And that is summarized right there. The a value, although not listed here, also tells you what the plot pattern is going to be. We use our 1, 4, and our 9, which are our vertical values for going out 1 from the vertex, 2 from the vertex, and 3 from the vertex, respectively. And that gets amplified or multiplied by a. The unique thing to this particular form is that it gives you the x-intercepts. So the s and t values, which are housed inside the brackets. The s and t values tell you what the x-intercepts, or the word we're going to be using interchangeably with x-intercepts, are zeros. So the s and t values tell you where your quadratic relation crosses the x-axis. And there's sort of two different scenarios here. The first is if your s and t values are different, we call that two distinct zeros or x-intercepts. So our example shows that we have x plus 4 and x minus 2, each binomial in brackets, and those tell us that our x-intercepts are negative 4 and positive 2. Now what I want to point out here is that while this looks like a negative 4 and this looks like a negative 2, the empty pared down version of our quadratic relation in factored form, these both have, let me just do a little erasing, it's getting a little crowded up in here. They both have negatives, which means that, similar to vertex form, when you have something that appears to be positive, let's do a little shout out over here, that's actually going to be x minus negative 4. That's actually, well, I should make that a square bracket again, I guess. Yeah, that's actually going to be minus negative 4. And then when we consolidate those two negatives, banging up together, we end up with what you see in the bracket, which is this perceived positive, but it is actually minus a negative value. Similarly, if our value looks negative, what we have here is x minus positive 2. So the perceived value of it is going to be negative, but it is actually minus positive 2, which is how we get the opposite of how they appear in these brackets are the actual x-intercepts or zeros. So going back to what I was saying, if s and t are different, you have two distinct zeros, meaning it shows up in two different spots. If s is equal to t, then you end up having two identical zeros. In this case, in the example, x plus 4 and x plus 4 gives you x equal to negative 4 and negative 4. So obviously you don't have to make that point twice. It just so happens that it only is one point. It just displays itself in factored form as having 2 points. They just happen to be the same. So working with this new form of a quadratic, let's go through a couple examples and we'll get some salient pieces of information. Because as before, anytime that we're trying to graph a quadratic relation, the most important piece of information to have is the vertex. And quadratic form doesn't, rather factored form of a quadratic doesn't give us the vertex straight away. We have to do a little bit of work for it. So let's work our first example. So here's our example, y equals x plus 2, x minus 4, both binomials in brackets. We want to state a, s, and t. So our a value, as always, is hanging out front. It's invisible, but it's a plus 1. The s value is one of the two values here, and it doesn't matter which one you pick as long as you get both between s and t. So that looks like a positive 2, but is actually minus negative 2. So negative 2 will be our s value, and x minus 4 looks like a minus, is actually a plus 4. So those are the x-intercepts, or zeros, as well as the a value. So now let's state this stuff. So the x-intercepts, zeros, are going to be, and I'm going to write these as points. It's going to be negative 2 and 0, and 4 and 0. The direction of opening with a positive a value, of course, is going to be up. Now, how do we calculate the actual vertex in this case? Because as I said, we need the vertex in order to actually put this thing on a graph. So to set this up, what I'm going to do is actually graph the 2 points that we've already have here, our two x-intercepts on the graph. So that's going to be negative 2 and 4. So I'm going to put these on the graph. There's negative 2, and there's 4. Now, what's interesting here is that what we know about parabolas is that they are symmetrical shapes, meaning that they are a perfect reflection along a middle line, and that middle line is our axis of symmetry. Now, visually, I can see that my axis of symmetry is going to fall halfway between these points, which is right here at positive 1. So I can actually dot in my axis of symmetry just using a visual cue, knowing that it is going to be halfway between my two x-intercepts. Oh, that's a mess. Let's tidy that up. X equals 1. Now, if you didn't have to graph this and you were just looking to find the vertex, there is a method that we can use to find the vertex, and it is an algebraic method. So to find the axis of symmetry, we want to find the h value, x equals h. We can actually take our two x-intercepts, add them together, and divide by 2. Essentially, that's what we did visually when we just looked at the graph. We're finding the average between these 2 points. So if we were going to just use this algebraic method, you would have h is equal to, now I do want you to note here, the s and t values are not the ones as they appear in the quadratic relation in factored form. They're the ones you take once you've drawn it out. So s is equal to negative 2, and t is equal to positive 4, all over 2. So again, that's a huge thing. I want to make sure that you note that we're talking about not these values here as they, let's change up the color a bit. It's not a positive 2, it's not a negative 4, it's the actual numbers. That's actually a negative 2, that's actually a positive 4. So those are the numbers that we use when we're calculating the axis of symmetry. And now we're just going to complete the math. We're going to finish the numerator. So negative 2 plus positive 4 is going to give me 2 over 2, which means my h is equal to 1, which we know visually we already did this. So how do we get the y component of that vertex then? Well, we take our equation. So we are going to find k. The way we are going to find k is subbing h into the equation. So once we have our h value being equal to 1, we can just sub that in. So we have y equals bracket x plus 2, x minus 4, and now we're going to do a substitution step. Our h value, as we now know, is going to be 1. So 1 plus 2, 1 minus 4. Work out the brackets. That's going to give us 3 and negative 3, which is going to give us negative 9. So the vertex then is going to be 1, negative 9. Write that down over here, my vertex, 1, negative 9. And now I can graph that point on my parabola as well. So we have 1, negative 9. That's going to be down here. It's on the axis of symmetry, which is as it should be. And now we can work our plot pattern. So our plot pattern, and again I'm just going to model that one more time, is going to be 1, 4, and 9. And remember, those are the vertical values when we go out 1 in either direction from the vertex, out 2 in either direction from the vertex, or out 3 in either direction from the vertex. And this 149 is going to be amplified by my a value. Now the a value happens to be 1 here, which means that it doesn't actually change the vertical values. So let's finish the graph. So we have from our vertex out 1 and up 1 on both sides, out 2 and up 4, 1, 2, 3, 4, and then out 3 and up 9, which as you see nicely corresponds to the x-intercepts we already have, and that's awesome. So we are going to now draw a nice curvy line through our points, making it curvy. Let's get some arrows on this thing, and let's get some labels. So as I said, we want to make sure that we're labeling our vertex every single time. That's going to be 1, -9. We're also going to label any intercepts that fall on integers. So over here we also have 0, -8. That's our y-intercept. And for our x-intercepts, we already knew these were going to be -2, 0, and 4, 0. And now we label the equation. Y equals x plus 2, x minus 4. And that is our graphed quadratic from factored form. So before we do example 2, I'm going to stop this video. Again, rewatch it to understand any parts that are, or to better understand parts that are unclear to you. I'll do the second example in another video, and we'll call it a day. So we'll see you in part 2.